So I'm gonna kind of move on quickly because we've slipped a little bit. So next up is Professor Libertad Barrón, calling from the Autonomous National University of Mexico.
Yeah, let me start. Sharing my screen. Let's see. It's this one. Can you see my screen?
Yes.
Okay, good. Okay, well, thank you very much for the opportunity to give this talk, and thanks, Austin, for organizing this nice workshop. So I'm going to talk about the implementation of the magnetic scalar potential method that Chris told us about earlier. And I'm going to give just one example of coils developed for fundamental neutron physics. Okay. So in fundamental neutron physics, we are interested in magnetic fields.
Your slides aren't aren't skipping.
Oh, is it not? So you are still in the first one, or?
Get PDF and.
Yeah, we're seeing the PDF viewer.
We don't see full screen.
Oh, I see. Oh, so I should not do full screen, right?
Share your whole screen, not just the app.
Yeah, I see. I didn't know that.
Yeah, I didn't know either.
Can you see the screen now?
It's blank.
It's black. No, we see blank screen. So you should share the application, either that application where you have this actual slide visible, or then share your whole screen.
Yeah.
There we go. It's good.
Yes.
It's good now? Okay. So too many options of screen sharing. Thank you.
This is perfect now.
Okay. So as I was saying, we are interested in magnetic fields so that we can transport and manipulate the neutron spin. So neutrons have spin, and also they have a magnetic moment that is proportional to their spin, is related to the gyromagnetic ratio. And when we apply an external magnetic field, this external magnetic field will exert torque on the magnetic moment and will produce the spin to precess around this external magnetic field with a precession frequency known as the Larmor frequency. When this external magnetic field changes, if it varies in space or in time, we can have an adiabatic process happening to the neutron spin if the fractional rate of change of the external magnetic field, which is given by this, is smaller than the precession frequency of the spin of the neutron about the magnetic field, or the Larmor frequency. This condition can be also expressed in terms of the adiabaticity parameter, nabla, is written here. So what we need for the interaction of the neutron spin with an external magnetic field to be adiabatic is that this parameter is much smaller than 1. Here we have the rate of change of the magnetic field with respect to the neutron propagation direction, we have the neutron velocity and the neutron gyromagnetic ratio. So it's a parameter that depends on the amplitude of the external magnetic field, its velocity of change, the neutron velocity, and the neutron gyromagnetic ratio. And what we mean by adiabatic is that the neutron will continue to precess about the magnetic field as it is changing with time or in space. So we have a way to manipulate the neutron spin in that way. We can change the direction of a neutron, of a polarized neutron beam using magnetic fields, or we can just use a holding magnetic field, a constant magnetic field, to transport the neutron polarization, to preserve the neutron polarization direction. So the example that I'm going to be talking about is a couple of coils that we developed for the neutron spin rotation experiment. The neutron spin rotation collaboration has developed a device that is capable of determining very, very small neutron spin rotations of the order of 10 to the minus 7 radians per meter. And this can be like determining these very small neutron spin rotations when neutrons interact with different targets in a region where we have virtually zero magnetic field. If a rotation of the neutron spin occurs, can help us to understand things of fundamental physics, like the hadronic parity violation, and to test the existence, or at least to put limits on possible long-range exotic interactions, either those that can be parity odd, or also some possible interactions that can be parity conserving, but that depend on the spin of one of the interacting particles. And here I have put some references where you can see more about this physics if you are interested. But what this device basically consists of a polarized neutron beam, which is polarized with a polarizer that is not shown in this figure. And then that polarized neutron beam is transported to the entrance of a magnetic shield region where we have virtually zero magnetic field. And so we need a magnetic field that's shown in these red arrows that is uniform and a constant magnetic field along the direction of polarization, which is the vertical direction in this case. And then in the case of a neutron spin rotation occurring, the neutron spin would acquire a transverse component that then we need to transport that transverse component and rotate it to the vertical component so that it can be analyzed in a neutron polarization analyzer. So basically what we developed are the input and the output coil for this device. The input coil is somewhat simpler because it only needs to produce a vertical component, uniform magnetic field. The output coil needs to produce a magnetic field that rotates from transverse to vertical along the length of the coil, but also it needs to have the possibility to produce clockwise and counterclockwise rotations so that we can, by alternating during measurements between these two states of rotation, we can avoid certain systematic effects in this type of experiments. So to design those coils, we use the method that Chris just described. I have here the equations that Chris explained very well. I'm not going to go into much detail, just to remind you that we can use the magnetic scalar potential to design the coils. we can find, if we know the geometry and we know the required magnetic field, we can solve the Laplace's equation to find the magnetic scalar potential, and that can give us the current paths that we need, or the windings that we need to produce that magnetic field. So in this case, our geometry was like this. We have an inner region with square cross-section. That's an empty region where the neutron beam guide, which is essentially a square tube, has to go inside that region. And this is the region where we need, for example, I'm going to take here the example of the input coil. We need a uniform magnetic field, a vertical and uniform magnetic field. Then the outer region is the return, that Chris also explained very well. We need to be able to force the magnetic flux inside this outer region so that we don't have straight lines of magnetic field around the room, and we do not disturb the magnetic shielding region. So we can use finite element methods to solve the Laplace equations for these two regions. Also, since we need to have the neutron guide inside, we cannot have windings, ideally, in the inner region. So we can divert this winding or this scalar potential to the outer region, and establishing these boundary conditions. We can establish a third magnetic potential with this boundary condition. It is equal to the first magnetic potential in this boundary, and is equals to 0, so that we don't have magnetic flux going out of that of those walls or of those boundaries. If we solve this and we consolidate the two windings, the one required to produce the return flux and the one required to produce the inner magnetic field, we end up with this. This is showing the surfaces of the equal potential, scalar potential, magnetic scalar potential. As Chris mentioned, what we care about are the contours that form in the intersections of the geometry and these surfaces. So these black paths are the winding patterns that we need to use to produce the desired magnetic field, which is a magnetic field that is uniform in the inner region, the square cross-section region, and the return flux that is forced inside this octagonal shaped outer region. And we use to solve for this and to find the winding patterns, we use COMSOL multiphysics. Then once we have the winding patterns, we can validate our coil and use Biot-Savart, also using COMSOL multiphysics, to verify that this produces the desired magnetic field. I will show you that in a moment. Before I show you that, I wanted to go back to these requirements for the neutron spin rotation apparatus, and to stress the fact that particularly for the output coil, we need two magnetic field components, two perpendicular magnetic fields. One transverse magnetic field that is fading as neutrons travel through the coil, and one vertical component that is increasing as neutrons travel through the coil. And also we need to be able to change the direction of one of the components so that we can produce clockwise and counterclockwise rotations of the transverse component of the neutron spin, which is the component of interest. Also, for the input coil, we decided to add a perpendicular magnetic field with a smaller amplitude. And that second component is something that we don't need to use for the measurements, but it is nice to have that feature so that we can produce control neutron spin rotations in the input coil. And in that way, we can analyze systematics of our apparatus. So that we also want to have a second component in the input coil. Here I'm showing again on the top graphs the input coil. You can see the winding patterns and the magnetic field that this should produce. Then in the two lower plots, I'm showing the one of the components of the output coil, just the transverse component. You can see that the winding density is higher at the beginning of the coil, and then is less dense at the exit of the coil. So this produces the tapered magnetic field that we need for that component. So it's a strong transverse magnetic field, and then it decreases along the length of the spin flipper. And we have something similar, perpendicular, for the other component. Again, we use COMSOL multiphysics to implement these current patterns and verify that we can obtain the desired magnetic fields before constructing. I will show you the calculated magnetic fields in a moment. I first wanted to show you some pictures of how we implemented these funny looking winding patterns for the construction of our coils. And this is actually the grad student that worked on these coils, Marisa Maldonado. And you can see here, so we decided to build a hollow structure with 5mm thick acrylic walls. Well, you can see there are some thicker support octagonal shape plates here, and then we have the outer walls, which were previously machined with a CNC to produce the grooves for the wire that following the current paths that we wanted, that we found in COMSOL that were appropriate to produce the magnetic field. Here are some other pictures of the process of assembling this structure. And you can see the grooves where the wires are placed. Then the next step is the winding. We have to wind this. We used in this coil gauge 18 aluminum wire and some glue, because in this was our first model using this method, our first coil, and the grooves were slightly bigger than the wires, and but for future coils we are actually now thinking of making grooves that have the appropriate size so that we can have to push, like apply some pressure to get the wires inside, and then we won't need to use any glue. They will they're mechanically attached to the walls of the coil. And then I mentioned we need two components of magnetic field, that they are superposed in the same spatial region, but we need two perpendicular components. So to obtain that, what we did was to add a second layer of acrylic to build something like a shells of coils. So after we had finished winding the first coil, we added a second layer and have the winding for the perpendicular component. And this is a picture where you can actually see the two layers of winding. You can see the bottom layer, since the acrylic is transparent, you can see the layer that is underneath. Thus, in the case of the input coil, the component we added to produce control spin rotations for systematic studies. And then you can see the front or the outer winding, which is the winding responsible for producing the uniform vertical magnetic field along this input coil. And I like very much this picture because it actually shows you what Chris has been saying, like since we have these contours represent, well, the intersection of the magnetic scalar potential surfaces. So these surfaces would just go inside the screen. And he was telling us how the magnetic field produced by these windings is perpendicular or crosses perpendicularly to each of these surfaces. So you can see here that actually the magnetic field produced by the red winding would be a magnetic field that is uniform inside. And it actually seems like it's a continuation of the green contours, which are the perpendicular scalar potential contours for that red contour. And then again, also the magnetic field produced by the green windings is something that looks like the complement of the red windings, is the perpendicular, which is the perpendicular to the green winding. You can see also that there is a different winding density in these two coils. This is because for the systematic studies component, the horizontal component, we don't want the same amplitude of the magnetic field. We want to produce small rotations in the neutron spin, small transverse components, and therefore we don't need a very strong magnetic field. This is showing the same, but for the output coil, which is the one that needs tapered magnetic fields along the length of the coil. So you can see how the windings start turning around before they go to the end, to the other end of the coil. You can see that here in different pictures. So we have a higher density of windings in one region and less density of windings in another region. You can see here when we started winding the inner shell of this coil. And here you can see now when the two layers have been completed. So you can see an inner coil that produces, in this case, a horizontal magnetic field or transverse magnetic field that is stronger at the entrance or in this end of the coil, and it's small or it's weaker at the exit of the coil. And then you can see also perpendicular winding. This produces a vertical magnetic field that is strong on the end where the horizontal field is weak, and then this is weak at the beginning of the coil. So this is how we produce the input and output coil for the neutron spin rotation experiment. This is these coils mounted on the apparatus designed to study possible spin-dependent exotic interactions. Here again, I'm putting the reference where you can see more about this. And then here I'm finally showing, this is the result of the calculation. So if you take these winding patterns and calculate using Biot-Savart what the magnetic field will, how the magnetic field will look like. This is the magnetic field along the axis for the input coil, the two components, vertical and transverse magnetic field. C axis is the neutron propagation direction. And you can see that they look very uniform along most of the length of the magnetic field. And one thing I guess I didn't stress enough is that we need to have adiabatic transport of the neutron spin for most of the length of the coils. However, in the regions where there is the transition with the magnetic shielding region, where the virtually zero magnetic field region is, we need to have a very sharp transition and non-adiabatic transition for the neutron spin, so that the neutron spin is preserved when the neutrons remain with the same orientation when they enter this zero field region, and also when they exit, we can still keep the same orientation of this acquired transverse component of the spin. So we need, in one of the ends of each of the coils, we need to have a sharper transition of the magnetic field, a sharp fall or a sharp rise of the magnetic field, depending on whether we are talking of the input or the output coil. And that can be produced with an end cap, as Chris was saying. We can compensate for the magnetic field not being the same as it is in, for example, in the center of the coil, by adding an end cap using these scalar potentials to determine the winding of this end cap. That would look like a kind of like a pancake. That's how they are called, pancake end caps. And these end caps can produce a magnetic field that is very localized, very sharp, and that together with the rest of the magnetic field produced in the coil can produce a much more sharp transition of the magnetic field. You can see here the red line is the magnetic field produced by one of these end caps at the exit of the input coil, and you can see the gray line is the sum of the vertical magnetic field produced by the coil and the end cap. And you can see here this non-adiabatic transition that we need in that transition from the input coil to the magnetic shielding region. So for those end caps, we also use acrylic, but since we could not have that material in the beam path for this experiment, we added a region or a plate of aluminum to complement the winding grooves. And then we have here a picture of one of those end caps with all the wires in already. Here I'm showing a comparison of the magnetic fields along the axis for the input and the output coil, for the two components of the field, and for the end cap. We only need a sharp transition in one of the components. In the case of the input coil, we only need the sharp transition in the vertical component of the magnetic field. So we only have one end cap to complement this magnetic field. And for the output coil, we originally only have a magnetic field in the transverse direction to transport the component of the spin due to the spin rotation. So we only need one end cap to complement that magnetic field. Here I'm showing first for the input coil how the magnetic field looks like along in the inner region, this square cross-section region where the neutrons pass through. This is the magnetic field, the vertical component, and these are the residuals. So the difference between the actual magnetic field and the magnetic field along the axis, which is the ideal, but as we go away from the axis, we expect variations. And you can see here for the input coil and for the two components of the output coil. You can see here how one of the components is large and then it's tapered as we go along the coil. And then for the other is the same, but in the opposite direction. And again, you can see the residuals. That's not, well, we can see that there are differences, but those are mainly near the regions where we have the current paths. For most of the volume of the inner region, we have residuals that are less than 10 milligauss for these coils. Here I'm showing the adiabaticity parameter that I presented earlier. The blue line represents the adiabaticity parameter for the input coil. This shows how we have adiabatic transport for the neutrons from the entrance through the exit, and then at the exit we have a non-adiabatic transition. That's when the neutrons enter the magnetic shielding region. And then for the output coil, we have a non-adiabatic transition at the entrance when neutrons exit from the magnetic shielding region, and then the transport after that is adiabatic. So to finalize, I wanted to mention again that both the adiabatic and non-adiabatic conditions for neutron spin transport are useful depending on the needs of the experiment. The magnetic scalar potential method that Chris has developed is a very powerful tool to design coils. Techniques like CNC machining as well as 3D printing can make it possible to implement complicated winding patterns using non-magnetic materials as support or as a structure for these coils. Particularly for neutron applications, we have found that aluminum wire seems to be the best choice, since this wire is more malleable, so it is easier to shape with these weird looking windings. And it's also less reactive to neutrons than copper, but also it is brittle. It can break easily, so that's one disadvantage of aluminum wire, but in general, we think is best for this type of coils. This technique is now being applied to several neutron physics experiments. We are developing coils for other experiments. In addition to neutron spin rotation, we have been using it for Noptrex. It's a time reversal experiment using neutrons and heavy nuclei, and also for neutron EDM. Finally, I want to leave this reference. Is the paper where you can find almost everything of what I told you today. You can find it in this paper. Thank you. Are there any questions?
Yes, I did. This is really cool. I might have missed this, but this is for like cold neutrons, right? So what do you happen to have any thoughts on how you would make this non-adiabatic transport work for like the ultra cold regime?
Oh, we have actually gone in the other direction. We have already built coils for epithermal neutrons. In that case, what you need is usually larger coils. You need more length in order to be able to achieve adiabaticity. But for ultra cold neutrons, I haven't had experience yet, but my I imagine that it would be even easier to achieve adiabaticity, because the lower the neutron velocity, the lower the adiabatic parameter. If I can maybe.
I guess the trouble with UCN is that they go back and forth between the target and the source. So you have to consider it, you know, multiple passes.
Yeah, that makes sense.
I'm more concerned about like the end caps, like in terms of fabrication. Do the UCN like have more trouble passing through this end cap type design, because you had coils stretched across, right?
Mm-hmm. You don't always need this. In this case, we wanted to have a non-adiabatic transition, but usually it's more common to have just adiabatic transport. That's usually the requirement. And in that case, you cannot avoid having end caps. But probably maybe Chris Crawford or Chris Swank can have more experience with ultra cold neutrons. I haven't developed any coil for ultra cold neutrons yet.
Well, I don't.
I know they can accelerate neutrons through through vacuum windows by using a very large field. So I imagine in one of those cases you'd want a current septum, and there's no way around it. If you want a large change in your field instantly, you need a current septum.
Yeah, there is actually the kind of what exactly where you want to have blocking matter, where it might be that the later ones on MRI and then on TMS, for different reasons, we have reasons to avoid having wires somewhere. So you can actually find slightly better compromises potentially with different optimization methods, where then of course I let that part entirely to whoever wants to think of any other uses, but we have other reasons to have wires not somewhere, and methods to try to find the compromise between where to put the wires and how to get still some feed characteristics that you want. Of course, you cannot entirely avoid that, but you might be able to get into your window far less obscurity or far less plugging.
Mm-hmm. Yeah.
I'd like to add that Gilles Caminero has done these DALI-like coils that have very large oscillations of current at the end caps and right just on the ends. And what that does is you can think of each oscillation as kind of a finger that goes in and pushes, kind of reaches in and makes very sharp field transitions.
Hi, Rasmus Setter here. I have a more practical question, perhaps, regarding the fabrication of these coils that you showed. So, thanks for the presentation and quite impressive work. So, if I phrase my question such that if you would now have to redesign and rebuild them, would you fabricate the coils in the same way, or would you? What lessons did you learn along the way?
Yeah. Yeah, I think one thing we learned is it's very hard to precisely place the different planes that conform your coil. So we tend to think that maybe 3D printing it's a better option. Maybe you can print already all the faces of your coil. Of course, in this case, it's a very long coil, but maybe it's easier to put together pieces along the length of the coil than putting all the walls and precisely placing them in the way you should. Also, what I mentioned during the talk, this was our first development, and we learned that probably we can do better with the groups. For example, 3D printing can give you the possibility of having groups that are round, and they can be half of the wire, half just like half of a circle in cross section, and they can even be slightly more than half of a circle, so that you can push the wire through, and they sort of clamp the wire in place. That also seems to be a good choice. And finally, I think well, I'm just thinking of different problems we had. I mentioned that aluminum is brittle, and we had a complication because once we build this outer layer of coil, the second layer, the inner layer is almost inaccessible, and our wire for the inner, in one of the cases, for the inner component broke. And it was very hard to repair because we had to make a hole on the acrylic and find a way to get in. So maybe particularly where the wire goes in and out, it would be better to have some reinforcement or have some sort of terminal where you take from there a different type of wire, not aluminum, because it breaks very easily. And finally, I think the end caps were causing some trouble because we didn't think of a way to mechanically attaching them. So it turned out to be very sensitive to the proper alignment of the end caps. So that's another thing, another lesson we learned for having a way to align to mechanically mount the end cap to the rest of the coil. But I think the main lesson I think is that we think now that 3D printing is a better choice for this type of coils. It's more precise, the placement of the winding paths.
Yeah, thanks a lot. It's things I haven't tried myself, and it's always nice to hear someone who has tried and what are the kind of, so we don't have to kind of go through the same process, you know. Yeah. Thanks.
Oh, welcome.
Hello, a bit of a smaller question. This is Cesare Tozza from Comsol asking. I've seen that you have used Comsol. Have you used the magnetic fields no current, or have you used the PDE mode?
Both. Usually to find the winding patterns, we use the PD module to solve the Laplace equation and find the contours of the magnetic scalar potential. And then that part is actually the most complicated in Comsol because we have to export the solutions, these contours, and then somehow in a new model, make them current paths, and then we use the AC/DC module.
I see. Because I have already mentioned Christopher, a contribution that we presented, I don't know, it was probably a couple of years ago at a conference. It was about completely different thing. It was about coil optimization, but high frequencies for induction heating. And so there was a skin effect. The model was about different things, but we used partially the same idea of using mixed formulation in that case, and use magnetic field no currents to carry the current and we implemented a slit condition, and since more or less that same release we support in magnetic field no current the option to to have also internal slits. So I was curious if how you use the console really technically, but more or less I understood. I understand also why you have this complicancy of creating, of exporting and reimporting the things. Probably there is a way of not if you generate a mesh, you can do everything inside one model. You don't. In that case, you probably don't need to export anything. But well, I don't know. If there, it probably really depends. It's a really model dependent.
Well, that's a good tip. I know that Christopher has been working on this. I think he has done some developments to make this process easier, but until now we are still struggling with that part of the process.
And Cesare, this is one related thing that I'm going to discuss, where I'll just give the brief version and then I'll give more detail in my talk in a little bit. But the issue that we tend to run into is that the contours that are exported by COMSOL are not oriented, they're not all oriented in the same direction. And typically it doesn't, with how we traditionally think about contours, it doesn't make sense to discuss the orientation or directionality of a contour line. However, in this case where the contour is an approximation of a current sheet, then the direction actually does matter. And we wind up spending most of our time finding the wires that are oriented correctly versus incorrectly.
Yes, that's painful, or then you need to be very careful when you are assigning current to each of the contours to assign the current in the right direction. What we do is we have two different currents, one positive and one negative, and we need to make sure that since the contours are in different directions, we need to check one by one that we have the appropriate current. So yeah, that's complication.
Let me make just a small comment. When you're putting your wires in, if you put them in well, if you can use MATLAB to program them in as paths, and if you do that, the direction will always be from the first point to the last point in your path, and so that can help out, especially using MATLAB if you have a huge number of points to put into these things.
Yes, and well, I think that actually there could be, because actually you should you know which is inside and which is outside, and you can orient the line using that information. And we do some things like those in some part of the coil geometry analysis, but it's well, I understand why you have difficulties. It's not you need to put some intelligence in your code for that. But are you presenting anything of this to the COMSOL conference? I don't know if I have not seen papers about this at the latest COMSOL conference, would say, but I don't know, maybe you did.
I submitted something like a couple of days ago, and I think Chris Crawford is also, well, Chris is also going to present something. But yeah, I submitted an abstract like a couple of days ago.
Good.
I think there was a paper about 6 or 7 years ago, maybe 8 even now, about the original.
Okay, thank you.
Great. Thank you, Libertad. Moving next is Dr. Chris Swank, who's joining us from